Hi, hello everybody. So today we are going to learn a very small topic, okay, which is orbital contribution to magnetic moment. Main heading, orbital contribution to magnetic moment. Okay, we have already learned about spin only magnetic moment, and we have done a few examples in the assignment questions as well, wherein we learned that the spin only magnetic moment represented as mu s, where s stands for the spin of the electron, that is equal to root of n into n plus 2, where this n corresponded to the number of unpaired electrons. Right? N corresponded to the number of unpaired electrons. So this contribution of the magnetic moment is only due to spin. Is only due to spin. Now let me say that you might know this. Any charged particle under motion, any charged particle. So the charged particle that we are talking about, any charged particle. So the charged particle that we are talking about is the electron. Okay? Under motion. So if it is moving, so our electrons also move. Our electrons move in two ways. So what we are trying to understand is any charged particle under motion will generate some sort of magnetic field. Some sort of magnetic field. Okay. And the strength of this magnetic field which is generated is calculated using magnetic moment. And that is what we have been trying to do. And then we are going to learn a little more deeper into that concept. So let's understand that what are the two types of motion. So we said that if you have an electron which is not moving, let's say you have some electron, it is not moving, so there won't be any magnetic field. But in our case, one electron that we consider has got two types of motions. Two motions. One is the spin motion. Spin motion. Spin motion means if you have an electron, it has its own axis and it can rotate either clockwise or anti-clockwise. Clockwise or anti-clockwise, it will rotate in its own spin. That is one type of motion which will generate magnetic moment. And the magnetic moment which is generated due to spin motion is written as mu s. S is the subscript notating the spin motion. Now, the second motion that it can have is the orbital motion. Orbital motion. So you have a nucleus at the center around which you have different orbitals. And in the orbitals, you have electron. And this electron will move around the nucleus. So this is a second motion. Understand that the earlier one which we said is the electron has got its own spin. Okay, that means it will spin in its own axis. This is a spin motion. Orbital motion is different. Orbital motion is where you have an electron and that electron moves around the nucleus in an orbital. Okay, and the orbital contribution. So there is some motion, electron is charged. So any charged particle under motion will lead to magnetic moment. So there is something called orbital magnetic moment represented as mu L. Mu L. Okay. But especially for transition metal complexes, which are mainly D block elements, mu S is what dominates. You will be learning about this in detail again, in depth, while we learn F block elements, where both of these are important. Mu S as well as mu L, both are important, but here it's not like that. Okay. So here the reason is, see, you have several types of orbitals. You have S orbital, you have P orbital, you have D orbital, you have F orbital. Correct? So the S, P, D are comparatively towards the inner side of an atom, and F is towards the outer side of the atom. So the magnetic field which is generated due to the electron motion in S, P, and D won't be felt that much. I repeat, if you have any atom, it has got S, P, D, and F orbitals. Electrons can move in any one of these, out of which S, P, D are towards the inner side and F is outer side, which means F is extended outwards. So if there is an electron moving, let's say there is one electron moving in the S orbital and it has generated some sort of magnetic field, which I'm showing by the yellow colored light. Sorry, yellow, I have highlighted in yellow, that is a magnetic field which is generated. So so you can see that the range of the magnetic field is very small because you have other orbitals. So the electron which is revolving inside the S orbital, even though there is some value generated, that is just quenched away. Not important. That is the same with PD as well. But in F, that is not the case. F is towards the outer side. If there is some magnetic field which is generated, that will be felt and that is significant as well. Okay, so we are talking about coordination complexes which are mainly D block elements. So these D orbitals come little inside. That means it is just prior to the F orbital and hence it is not that significant. The orbital contribution is not that significant. But it becomes significant in certain cases. And which are those cases? Okay, so I hope the concept is clear. I repeat again, you have the nucleus, you have S, P, D, and F orbitals, out of which the S, P, D, and out of these four, if you have electrons in S, P, and D, as the electrons are moving in the innermost orbitals, the orbital moment, the orbital magnetic moment is not felt that much. But if you have it in F, it will be significant enough, and that you will be learning the equation, everything you will be learning in F block elements. Okay. Now we are talking about the case where the electron is moving inside a D orbital. And when does the orbital magnetic moment become significant? Okay. So there exists a orbital magnetic moment if there is an unsymmetrical electron distribution in T2G only. Important, I'll explain it. So in most of the cases of the D block elements, we consider mu S only. But in certain cases, you will have to consider mu S. Along with the spin, you will also have to consider the orbital magnetic moment. So when does this orbital magnetic moment contribute? That is when you have an unsymmetrical electron distribution in T2G. Okay? That is the reason. So it is said that okay, let me give you some examples. Let's say you have D1 system. So if you have D1 system, it is T2G1, correct? Unsymmetrical electron distribution is what you have, and hence this will show contribution due to orbital magnetic moment. Let's say you have D2, T2G2 it's going to be, which is also unsymmetrically distributed. This will also show orbital contribution. Let's say you have D3, which is T2G3. Oh, sorry, I have written 6. T2G3. So here if you can see, this is a symmetrical distribution and hence no orbital contribution. Let's say you have D4 high spin. So if you have D4 high spin, you have T2G3EG. Now see, for orbital contribution, you are not at all concerned about the unsymmetry in EG. You are concerned about the unsymmetrical electron distribution in T2G only. So here we can see that there is no kind of unsymmetry, and hence here also there won't be any orbital contribution. But let's say you have D4 low spin. Okay, so it would look something like this. 1, 2, 3. Fourth one cannot jump and will get paired over here. T2G4EG0. Now there is an unsymmetrical electron distribution and hence orbital contribution exists. Okay, next is D5, high spin, let's say. So if it is high spin, you have 1, 2, 3, 4, 5. T2G3EG2. No unsymmetry and hence no orbital contribution. D5LS, you try it on your own. 1, 2, 3, 4, and 5. There is some sort of unsymmetry and hence orbital contribution exists. Let me draw D6 together. High spin, low spin. So D6 high spin is where 1, 2, 3, 4, 5, and 6. Unsymmetrical electron distribution at T2G and hence orbital contribution will exist. While over here, if you can see, this is 1, 2, 3, 4, 5, 6. Symmetrical electron distribution and no orbital contribution. Okay, so I hope you understand. If there is some sort of unsymmetry in T2G, that is all that you have to test for. D7 high spin and D7 low spin. You can try it on your own. So 1, 2, 3, 4, 5, 6, 7. There is some sort of unsymmetry, orbital contribution exists. Here 1, 2, 3, 4, 5, 6, 7. Unsymmetry is at EG, that does not matter, and hence no orbital contribution. Right? Next, D8. No matter the way you fill, always it will have two unpaired electrons, whether it is low spin or high spin, it will always have two unpaired electrons in EG only. T2G will be completely and symmetrically filled and hence no orbital contribution. D9, to the same system, you will add one more electron at EG. Again, you will see no orbital contribution because you don't have any sort of unsymmetry at T2G. D10, we need not do because it is completely filled, completely symmetrical, and hence again, no orbital contribution. Okay, so this is the concept that you'll be using to solve the problems. If there is any sort of unsymmetry at the T2G, that's when you see an orbital contribution. Otherwise, you need to consider spin-only magnetic moment. I hope it is clear. I repeat again, the orbital contribution exists only when there is some sort of unsymmetrical electron distribution at T2G. Okay. Now, until now, only these concepts have been asked, but just note that what are the reasons? What are the reasons? So, T2G, so the main reasons are, we know that you have dxy. We know that we have dxy orbital. So, let's say this is x-axis, this is y-axis. dxy means this is how it is. Your lobes of the d orbitals will lie in between the axis. Now, the moment you rotate these lobes, if you rotate it, at 45 degrees, what will happen? Only the lobes. My axes are the same. I'm just rotating the lobes. Now, your T2G, so this was actually dxy, which belonged to the T2G of the octahedral geometry. Now, after rotation, this has become dx squared y squared. Correct? So 45-degree rotation of dxy, which is one of the member of the T2G, has now been converted to dx square y square. So your orbital conversion has happened. So if there is some sort of orbital conversion, that will lead to orbital magnetic moment as well. This is actually the theory which is there in Huey, Housecroft, whatever you take. The concepts that you have to take forward for solving the problems were already discussed, but this is the theoretical portion if they ask. Okay, this is a theoretical. Similarly, let's say that you have x-axis, z-axis, and you have xz. This is the xz. The moment you rotate this one at 90 degrees, 90 degree. So the orbital rotations over here are interchanging the d orbitals as a whole. So the moment you rotate this, we know if you rotate it at 90 degree out of plane. So this is x, this is z, and of course this is going to be y. The dotted line is going to be y. So if you rotate it out of plane, xz, instead of xz, it will become yz. It is difficult to draw it over here. Okay, but then what you're going to get is actually yz. Please imagine it in a 3D way. You already know that x, z, y, all of these are perpendicular to each other. So if you rotate this xy at 90 degree, what you're going to get is a yz. So what has happened? This dxz is also a member of T2G orbital. Correct? So mainly when you have T2G orbitals like dxz, dxy, and this one is, now it has become dyz. Correct? This one also. So these three orbitals which are a part of T2G upon rotation gets converted into some other sort of orbitals. I hope it is clear. I'll summarize it over here. If you have dxy and if you rotate it at 90 degree, this will become dx square y square. Non-axial orbital has become an axial orbital. Let's say you have dxz, not 90 degree, 45 degree. Let's say you have dxz. If you rotate it at 90 degree, it becomes dyz. Similarly, if you have dyz and if you rotate it at 90 degree, it becomes dxz. Okay, because of these conversions, what happens is their magnetic field generated becomes more strong or more prominent because already there is a motion. Apart from that, being a geometry, we already know that the electron-electron interactions between the metal and the ligand along the axis, in between the axis are all different. So it is mainly because of the interconversion due to orbital rotation. Interconversion due to orbital, in case you get a theoretical concept. Interconversion due to orbital rotation that leading to orbital magnetic moment. Okay? So I'm not sure if you had noticed it. We had done a problem in one of our assignments where they said that the total magnetic moment of a complex COF63 minus is 5 Bohr magneton. This was how it was written. Okay, now we already know that COF63 minus, no, it was not COF63 minus. I need to check. Let me check the question, please. This one. Yeah, COF6 only. Okay. Yeah, it was the same complex. Okay. So here we know that cobalt is in +3 oxidation state. fluoride with cobalt will act as a weak field ligand, and the way you will distribute your electrons, which corresponds to a configuration of D6 in T2GEG, is going to be 1, 2, 3. Fluoride is going to act as a weak field ligand, 4, 5, 6. This is how you are going to actually fill the electrons. Okay. Now, if you consider spin only magnetic moment, what you will be getting is n into n plus 2. So there are 4 unpaired electrons. If there are, just a second, please. I'm so sorry. So if there are 4 unpaired electrons, 4 into 4 plus 2, correct? 4 plus 2 is 6, root of 24. You will get this value as approximately 4.8. But you can see that your value is not 4.8, it is slightly higher. Why is the value higher? That was not the question. The question was entirely different. But I'm just saying that over here, the elevated value of the total magnetic moment is because you have some sort of unsymmetry in T2G. As a result, there is some sort of orbital contribution. So when along with mu s, you also add mu l, that's when you get your final value. So 4.8 plus a small value is what you have to add. And that orbital contribution is due to the unsymmetrical electron distribution at T2G. Okay, I hope you have got the concept. I had one more question. Let me check. One more which was asked. Let me see. So in that question, different configurations were given. Yeah. The question was this. Spin orbit coupling. Spin orbit coupling is shown in. So spin orbit coupling means you will have spin motion which leads to some sort of magnetic moment. Along with that, magnetic moment due to the orbital motion is also contributing. So both of them have now combined and you're getting a total magnetic moment. That is the meaning of this question. Okay. 4 options were given. T2G6 EG2, T2G6 EG0, T2G4 EG0, T2G3 EG2. So you have to know that if you need orbital contribution due to magnetic moment, if there must be some sort of spin orbit coupling, what you have to check is the unsymmetrical electron distribution at T2G. So here T2G is fully filled, here also T2G is fully filled, here T2G is exactly half filled. So it's not A, B or D, instead it is C, because you have 4 electrons in T2G and there is some sort of unsymmetrical electron distribution that leads to orbital magnetic moment as well. Okay, so actually in this complex, if you calculate mu s only, there are only 2 electrons which are unpaired. So root of 2 into 2 plus 2, you're going to get a value which is approximately around 2.8. But if you experimentally calculate the magnetic moment, it is going to be definitely higher than 2.8 Bohr magneton. Why? Because you have orbital contribution due to the unsymmetrical electron distribution at T2G. I hope you have got the concept. That's all about this video. A very small concept. That's it. See you in the next.